Okay, this is the last video for our first set of notes section on sections 12.1 and 12.2. We are on example 8 on page 8. So we have all the information necessary to work through this example, so let's just talk about it. In example 8, you're given the vector v, which is 3i minus 4j. Now, this could be a two-dimensional vector in just the xy plane, or you could think of it as a three-dimensional vector where the kth component or the third component in the z direction is 0, but doesn't really matter. All the formulas work the same no matter how many spatial dimensions we're in. So let's say that's a velocity vector. Express v as a product of its speed times its direction of motion. So if you remember back from Calc 1, speed is the absolute value of velocity. Well, it's the same idea here. Speed is the absolute value of this velocity vector, or that means the length of the velocity vector. So that would be the square root of each component squared and added up. So 3 squared plus a minus 4 squared, take the square root and you end up with 5. So the speed is 5. And imagine something going 5 miles an hour. It doesn't give you any direction. Now what is the direction? So whenever you're said a direction of motion, you're supposed to indicate it in terms of a unit vector. So we just need to turn v into a unit vector. So remember, direction would just be v divided by its length. That will give me a unit vector. So 3i minus 4j divided by its length of 5 would be 3/5 I minus 4/5 j. So this was kind of a, just a understanding of vocabulary example more than anything, because notice that this just says v equals v because the magnitudes or the lengths could cancel out. But when you write it times its magnitude times its direction, right? The magnitude is the length, the direction is making a unit vector. This is the way to write it. So 5 times the vector 3/5 I minus 4/5 j. So there's no more examples in here, but I just want to make a couple notes. In summary, if the vector v is not the zero vector, then v divided by its own length is a unit vector called the direction of v. And the equation v, the vector v, which is its length times its direction, magnitude times v over magnitude, expresses its vector v as its length times its direction. And then we don't really need to do an example on this, but I did want to talk to you about the midpoint of a line segment. It's an easy extension from what you know from basic algebra to find the midpoint of a line segment. But if I'm in 3 dimensions, it may seem like it's not an easy extension, so let's see how it works. It's usually done by looking at vectors, believe it or not. It's helpful to seeing how the formula works. So if I want to know what's the midway point between the points P1 and P2, I want to find this M here. How do I find M? Well, basically I want to think about what is the vectors 0 to M, where 0 is the origin vector. Okay, this is the 0 vector, but that means it sits at the origin. Okay, so how does that work? From O to M, well, that's the same thing as going from O to P1, and then from P1 to P2, but not all the way, only halfway to the midpoint. Right? So I don't know if you remember from adding vectors back in high school or wherever else you might have seen it, but if you want to add vectors geometrically, you take the initial point of the second vector, put it on the terminal point of the first vector, have it go over, and then this vector from the place you started to where we're ending adding the vectors is called the resultant vector. And it's the length of that resultant vector that we're interested in, okay? Or actually, what are the components of it, because we're interested in what the components of M are, not the length, sorry. So what is this vector OM? Just what we talked about. But what is half of P1 to P2? It's half of 0 from P1 to 0 from P2, right? Does that make sense? Why is that? I mean, subtracting those, right? If I go 0 P2 and then I subtract 0 P1, it's like I could take this over here, put it over its initial point here, but you're going backwards because we're going in the opposite direction minus. So it's down here. So that's this vector right here, which you can't see, but it's the same vector as this long one from P1 to P2. Okay, so now what is OM? It's this. So now you can easily see through basic algebra here, right? I have OP1 minus a half OP1, so that's a half OP1, and then I still have a half OP2. Now what are these guys? O to P1 is just x1 plus x, is this x1, y1, z1, right? From O to P1. From O to P2 is just x2, y2, z2. So when I add their components, I get x1 plus x2, y1 plus y2, z1 plus z2. Take half of that, and lo and behold, there's a midpoint formula that we're used to. So the midpoint m, this is the vector OM, but the midpoint m would just be the terminal point, which is x1 plus x2 divided by 2, y1 plus y2 divided by 2, z1 plus z2 divided by 2. And that ends our section 12.1 and 12.2 notes.